Hi guys, it's Mrs. Allison. Today we're going to look at tangent planes and linear approximations as it relates to multivariable functions. So we know to be differentiable that if the partial derivatives exist near a point, then f is considered differentiable. So if the partial derivatives with respect to x and with respect to y exist, then we call f differentiable. Now, if it's more variables than just the two, we would need each of the partial derivatives to exist. Now, that's important because think back to single variable calculus. When we talked about local linearity, we said that several things needed to be true in order for us to be able to find local linearity. Is that the function needed to be differentiable, and it needed to be a smooth curve. Okay, differentiable and smooth. And we know to find the equation of a tangent line in single variable calculus, we needed a point, and if we let that point be the ordered pair a f of a, and a slope, because that's what we need to write the equation of the line, we would take the derivative of the function evaluated at a. Then we could write the equation of the tangent line, which would be y minus the y value, f of a, equals the slope, the slope times x minus a. And so then we would say the linearization of this is the capital L of some, let's not call it A, let's just call it capital L, equals f of A plus the slope, x minus a, which then we could say that if I wanted to approximate some value of the function f, I could take this linearization and the value would be the approximate value for that function. Remember, this is a technique we can use to find the value of a function if we don't know the function, but we know its tangent line at a point. Now we're going to extend those ideas today to the function of several variables. Okay, so suppose we have a surface in 3 space that has the equation z equals f of xy, where f has a continuous first partial derivative, has continuous first partial derivatives, and we let point P be some point on the surface, just any random point on the surface. Then if we let C1 and C2 be curves obtained by the intersection of the vertical planes, x and y, with the surface of S, then we let T1 and T2 be the tangent lines to the curves C1 and C2 at the point P. The tangent plane to the surface S at point P is defined to be the plane that contains the tangent lines T1 and T2. Okay, so picture this graph here, and if we have a point, so here's my point P. Okay, and if we have some curves that are obtained by the intersection of vertical planes, whatever we let y equal, whatever we let x equal, so we have a curve here, and we have a curve here, and where those curves intersect, they're on that surface, the blue surface, where those curves intersect. If we draw the tangent lines, and those tangent lines are the red lines here, to the curves, so T1 would be tangent to C1, T2 would be tangent to C2. Where those curves, or where those two lines are, make the plane that's tangent to the surface at the point P. Okay, so what I want to do is I want to now look at this video real quick, just so you can see this applet. Okay, so the link that you have on here takes you to this webpage. And it has a pretty cool applet that you can play with hold on, let's see if I can drag it around. It's not very responsive on this. Let's do this. Let's look at a movable tangent plane. And if we take and move the x coordinate, you can see the plane moving through there, the tangent plane. Or if we move the y coordinate, you can see it changing. So we can change the y and the x coordinate, and you can see what that tangent plane would look like, and how it would be relative to the tangents at that point. Now, this is obviously a pretty crazy example, but I wanted you to see what that looks like. So that's a tangent plane. So then how do we find that? When we want to find the equation of a tangent plane, remember the equation of a plane in general is the equation if we have a x minus x naught plus b y minus y naught plus c times z minus z naught, where we have our directional derivative, that's not what I mean, where we have our direction vector. We're going to get to directional derivatives here in a little bit. We have our direction vector as well as the initial point. So when we want to find the equation of the plane through the point P without dealing with vectors and cross products, because we could certainly use those as well, we would use the formula z minus z naught equals the partial derivative of f with respect to x times x minus x naught plus the partial derivative of y at the point y minus y naught. Oh shoot, go back. These should be x naught, y naught. Let's look at an example. Let's find the tangent to the plane, tangent plane to the elliptic paraboloid z equals 2x squared plus y squared at the point 1, 1, 3. Okay, so in order to do this, the first thing that we need to check is we need to check it's actually differentiable at that point. So we need to check that both of our partial derivatives work. And the beauty of checking to make sure that the partial derivatives exist is that then we have the partial derivative. So it makes it easier to substitute into the formula. So let's do the partial derivative with respect to x. And if we take that partial derivative, we would get 4x plus 0. And if we take the partial derivative with respect to y, we would get 2y. And since both of those exist, the partial derivatives exist, we know we can go through this process. And what I'm going to do now is I am going to take the partial derivative with respect to x of the point 1, 1. So we would get 4. And I'm going to take the partial derivative with respect to y of 1, 1, because 1 is x naught and 1 is y naught, according to the point. So we get 2. So then the equation of the plane that I would get would be z minus 3, z minus z naught, equals my partial derivative evaluated at that point, 4, times x minus x naught, plus the partial derivative evaluated at the point y minus y naught. Now, this is an acceptable form to have it in, but you may see it simplified, well, several different ways. We could put the 3 in the front, so 3 plus 4 times x minus x naught plus 2 times y minus y naught, which is 1. You may see it this way. This is probably the most common way you would see it. It is possible because we have looked at planes in the past, and when we looked at planes in the past, we combined all like terms. So it is possible to get a plane that looks like z equals 4x plus 2y minus 3 as well. So that is how we find the tangent plane to the elliptic paraboloid at the point 1, 1, 3. Now, when we talk about linear approximations or local linearization, was what we called it in 2 space, So in single variable calculus, the tangent line is a great way to approximate values, and the same is true with the tangent plane in multivariable calculus. So if we look at our tangent plane from the last example, we had z equals 3 plus 4 times x minus 1 plus 2 times y minus 1. We're going to go with that form. And if we look at that as it relates to the function of two variables, we would say that the linearization, remember linearization is at capital L, equals the function evaluated at the point x naught, y naught, plus the partial derivative of x evaluated at the point times x minus x naught, plus the partial derivative of y evaluated at the point x naught, y naught, multiplied by y minus y naught. Oops. And that is the equation for the linearization. Now, if we want to use that, let's go back to that problem before, use it to approximate the values of f of x near 1, 1. Well, we would expect that we would see 3. But let's say I wanted to find, let's do the linearization of 1.1. I'm going to scoot this up. So what it allows me to do is it allows me to take this function and approximate any values of f of xy near the point 1, 1. All right, let's look at an example where we put this all together. I want to first show that f of xy is equal to xe to the xy, that it's differentiable at 1, 0. Now keep in mind, to be differentiable at a point is very different than differentiable throughout the whole function, and it's much easier to show it's differentiable at a point. So to show it's differentiable at a point, we just want to show that that partial derivative exists at that point. And then what I want to do is find the linearization of f of xy and use it to approximate f of 1.1 comma negative 0.01. Okay, so the first thing that I'm going to do is I am going to show, or I'm going to attempt to show, that both the partial derivative with respect to x and the partial derivative with respect to y exist. So let's show that. So let's do the partial derivative of f with respect to x. We would need to use the chain rule on this one. So we would get e to the xy, derivative of the first times the second, plus the derivative of the second, which would be y e to the xy times the first. And if I go ahead and evaluate this at 1, 0, because that's the original point, we get, when I plug in 1, we get 1 plus 0, so we get 1. So the partial derivative of x is 1 at that point. And let's do the same thing for the partial derivative of y. Partial derivative of y, we do not need a chain rule, or sorry, a product rule, because x is held constant. So we would get x e to the xy times the chain rule. So the derivative of xy would just be x. Well, let's simplify that to be x squared e to the xy. And if I evaluate that at the point 1, 0, if I evaluate that at the point 1, 0, 1 is x squared, we'd get 1 squared e to the 0, so 1 squared, which is 1. Okay, so we know that got real messy. I'm going to rewrite that. What we know is that the function is differentiable at the point 1, 0. Now to find the linearization, what we're going to do is we're going to write the linearization equation. And remember we said to do that, the linearization is going to be the value of the function at the point. Well, we didn't find that. So this needs to be f of x sub naught, y sub naught. So f of 1, 0. So if I want to find f of 1, 0, I'm going to come to the side. And I would get 1e to the 0 power, which is 1. So for my linearization, this piece is going to be 1. So we have the linearization is 1 plus the partial derivative with respect to x, which is 1, evaluated at the point. And then the partial derivative with respect to y, evaluated at the point, is 1, y minus 0. So this is my linearization, meaning I can make pretty good approximations for my function based on this linearization. Well, now what I'm going to do is I'm going to evaluate that. And I'm going to evaluate it by saying that if I want to find what the value of 1.1 comma negative 0.1 is, I'm going to say it's going to be approximately 1 plus 1 times x, which is 1.1, minus 1, plus 1 times y, minus y1, y naught. And when I simplify this, we get 1 plus 0.1 minus 0.1, and so we get the linear approximation is approximately 1. What that tells us is that most likely, if I looked at an ordered triplet, it would be 1.1, negative 0.1, comma 1. This would be the ordered triplet that we'd have. That would be the point on the surface. Okay, so hopefully you see that they look very similar to what we did in Calculus 1 or Calc AB, Calc BC for you guys right at the beginning, or an honors trig pre-calc when we did the linearization. So not much different when it comes to planes. We just have to use partial derivatives. So you guys have a web assignment that goes with this, and we will see you tomorrow.